Dear students, in the previous classes, we have discussed a diverse number of topics, such as sampling, descriptive statistics, probability theory, discrete and continuous random variables, and normal distribution. A diverse number of topics. Now, we consider how these seemingly diverse topics can be integrated to lay the groundwork for what is known as inferential statistics or statistical inference. As it is well known to you, statistics is a science of inference. It is a science of generalization from a part means sample, to the whole means the population. So it is a science of inference, and it is a science of generalization from a part to the whole. And from sample to population. And as we have defined earlier, population is the entire collection of measurements of a variable we are interested in. For example, the number of students in a university, the height of the population in a country, or number of households in a country, etc. Population. And the sample, as we have defined earlier, is a subset of the population. A subset of the population. And this sample is used to make inferences about the population. And we have discussed in detail how to collect sample, random sampling procedures, etc., etc. Now, a population may be large. Sometimes it is infinite, so that it is impossible to collect information from each and every unit. So, to make inferences about the population, we use sample statistic, or known as estimators, to make inferences about population characteristics known as parameters. As population is large and sometimes infinite, it is impossible to collect information about each and every unit of the population. To obtain information about the characteristics, the parameters of the population. So what we do is, we collect a sample from the population and we estimate some quantities from the sample known as sample statistic or estimators to make inferences about the population. And as we have discussed earlier, the population has a frequency distribution. And we have defined what is a frequency distribution for a discrete random variable and also for a continuous random variable. And it is nothing but the distribution. The frequency distribution is nothing but the frequencies of occurrence, the distribution of the frequencies of occurrence of the elements. The population distribution, when stated in relative frequency, is also the probability distribution. As stated earlier, frequency distribution, when expressed in percentage terms, relative terms, is known as probability distribution. Now we have studied in detail the probability distribution of discrete and continuous random variables and also the characteristics of probability distributions, namely mu and sigma square. Population has a frequency distribution. This frequency distribution, when expressed in relative terms, is nothing but the probability distribution. And we are not interested in the entire probability distribution. We are interested in some of the characteristics of the probability distribution. And these characteristics that we have discussed in detail are mean and variance. And this mean and variance are known as the parameters. And what is a parameter? A parameter is a numerical measure of the population. A numerical measure of the population is called a parameter, or simply is called a population parameter, or simply a parameter. So a parameter is a numerical measure of the population. And our aim is to make inferences about parameters such as mu and sigma square. And inferences about these parameters are made using sample statistics. Sample statistics, or what is known as estimators. So estimators or sample statistics are used to make inferences about parameters. A parameter is a constant, whereas an estimator is, or a sample statistics is, a rule or a formula which tells us how to estimate the population parameter. For example, x bar is a rule or formula which tells us how to estimate a population parameter mu. Similarly, S is equal to root of sigma x minus x bar square by n minus 1 is a rule or formula which tells us how to estimate the population parameter sigma, standard deviation, population standard deviation. So our aim in statistics is to make inferences about parameters using sample statistics. And the sample is as we have studied subset of the population. And as we have seen earlier, when a sample is used to obtain information about a population, we take a selected number of observations, say 50 or 60 or 100 like that, and it is sensible to use a sample to make information about parameter than conducting a census. To obtain information about population parameter, you can conduct a census, but it is more sensible to conduct a sample to make inferences about parameter, because a sampling procedure is less costly, or maybe because sampling can be conducted more quickly. So sampling is generally preferred over census to gather information about population parameters. But when we use sampling to make inferences about population parameters, we must always keep in mind one particular problem. The problem is because sampling from population provides data for only a portion of the population, we cannot expect that sample yields perfectly accurate information. We cannot expect that sample yields perfectly accurate information, because sample is based on a part of the population. It is not based on the entire population. So whenever we use sample to make inferences about population parameters, a certain amount of error may result, and we call this error sampling error. We call this error sampling error. Sampling error is defined as the error resulting from using a sample to estimate a population characteristic. Sampling error is defined as the error resulting from using a sample statistic to estimate a population characteristic. And in order to understand what is sampling error, we have to explain what is known as sampling distribution. Sampling distribution of the sample statistic. Whenever a sample is used to gather information about a population parameter, there is always sampling error. And in order to understand what is sampling error, we must first explain the sampling distribution of a sample statistics, or what is known as the sampling distribution of an estimator. Now, let me first give a formal definition of what is sampling distribution. The distribution of a statistic is called the sampling distribution of the statistic. the distribution of the statistics. That is, all the possible observations of the statistics of a given sample size. That is a point which I will explain later. The distribution of a sample statistics is known as sampling distribution, and it is the distribution obtained from all the possible samples from a population of a given sample size. And sampling distribution is a probability distribution. Sampling distribution is a probability distribution where the sample statistics or the estimator is a random variable. So remember this. We consider the estimator like a mean, like a variance, etc. as a random variable. So estimators have probability distributions, and this probability distribution is known as sampling distribution. Now, we consider in this section the sampling distribution of the sample mean x bar. We can derive the sampling distribution of all estimators like a sample mean, sample standard deviation, sample correlation coefficients, sample proportions, etc., etc. Now we concentrate on the sampling distribution of the sample mean. Remember this, we consider the estimator as a random variable. Naturally, it has a distribution, a probability distribution, and the probability distribution of the estimator is known as sampling distribution. So, let me define what is the sampling distribution of x bar. For a variable x, and also for a given sample size n, for a variable x and also for a given sample size n, the distribution of the variable x bar, the distribution of the variable x bar is called the sampling distribution of the sample mean. For a variable x and a given sample size n, the distribution of x bar is known as the sampling distribution of sample mean. And sampling distribution of the sample mean is a probability distribution where the random variable x bar take infinite number of values equal to the number of samples taken. So, for inferential statistics, we use samples, and whenever samples are used, there is possibility of sampling error because x bar will not be equal to the parameter. So in order to understand sampling error, we use the concept of sampling distribution. And sampling distribution is nothing but a probability distribution. Probability distribution where the random variable is an estimator. Now in order to understand sampling distribution more accurately, sampling distribution of the sample mean more accurately, let us consider a simple example. Suppose that the height of 5 individuals in inches is given as 76, 78, 79, 81 and 86. Suppose that in the population there are only 5 individuals, and naturally population mean mu is sigma xi by n is equal to, adding together this, dividing with the 5, you will get it as 80 inches. This is a very unrealistic example. Population has only 5 members. Now suppose that we take all possible samples of 2, 76, 78, 76, 79, 76, 81, 76, 86, 78, 79, 78, 81, 78, 86, 79, 81, 79, 86, and 81, 86. And suppose that we calculate mean for each samples. You will get 77, 77.5, 78.5, 81, 78.5, 79.5, 82, 82.5, and 83.5. All the possible samples of n is equal to 2 has been taken, and each time the arithmetic mean is calculated. And as you can see, these are the estimators of 80. And as you can see, of the 10 values of x bar, none of the values is equal, only one value is equal to 80, one value is 77, one value is 83.5. So the range of x bar is from 77 to 83.5. 83.5. And if you calculate the frequencies here, in this case, each x bar take only one value, 1, 1, 1, 1, 1, 1, 1, etc. So that the relative frequency is 0.1, 0.1, like that, 1, 0.1, as x bar take only one values. Now, of the total of 10 samples, 3 lie between 1 inch above and below the mean. That is 80, then 81, 89.5. That is 80, 81 and 79.5, close to 80. Other values are beyond this. Similarly, if you take samples of 4 each, if you take samples of 4 each, so for example 76, 78, 79, 81, and you can take 5 possible samples like this, and x bar is in this case 78.5, 79.75, 80.35, 80.5 and 81. You will see that 4 values lie between 1 inch below or above 80. So as the example shows, as the sample size increases, let me draw this in the form of a, suppose this is the position of mean 80. This is the distribution of x bar. If n is equal to 5, only 1 point x bar. If you have x bar, n is equal to 4, it has more spreads. If x bar, n is equal to 3, the spread increases like this. Again, so as the sample size increases, the value of x bar is close to the population parameter. As the sample size decreases, the value, the spread of x bar around mu increases. Anyway, that is a point which we will see later. Now, for the time being, if you have, say, a population equal to 5,000, and if you take 50 samples, the number of combinations you can take is 5,000 n 50 is a huge number, as it is known to you, 5,050 number of combinations. Suppose that you can take, say, 5,000 samples, so that you will generate 5,000 x bar and associated frequencies. And if you take the relative frequencies, this relative frequencies is the PDF. And this PDF is known as the sampling distribution. And as we will see later, for arithmetic mean, the sampling distribution will be something like this, with a specific mean. So this distribution, that is the distribution of the estimated distribution of x bar, is known as the sampling distribution. Sampling distribution. And this sampling distribution is used for hypothesis testing. Always remember this. Sampling distribution is very important in inferential statistics. The entire hypothesis testing procedure is based on the sampling distribution. And the sampling distribution is the distribution of the sample statistics. And it is a probability distribution where the random variable is the estimator. And as the sample size increases, the distribution gets more and more concentrated around the mean value. So the spread of this sampling distribution, as is clear from this presentation, depends on what is known as the sample size, a point which we will see later. So this is the concept of sampling distribution, specifically sampling distribution of the sample mean. You can derive the sampling distribution for any estimator, and it is used for inferential statistics and hypothesis testing.